Okay, so what we're going to do is we're going to review how we did the orbital overlap diagrams based on our valence bond theory. Now remember, when we did these, we had a number of steps that we had to keep in mind. Our first step being that we needed to do our Lewis structure so that we would know the bonds and types of bonds that form between the atoms. Then we needed to know our valence electron configuration, and often for this we used both a combination of the shorthand and the energy level diagrams. We would show any hybridization that might have occurred. Then after we had our hybridization, we would show our overlap of orbitals. And then once we know our overlap of our orbitals, then what we can do is we can draw the structure. Okay, so let's take a look at our first one, BrCl3, or bromine trichloride. So as we stated, the first thing we need to do is our Lewis structure for this molecule. So we know that our bromine is our central atom, and so if we do our so we have this. So now we know our Lewis structure. We know that we need 3 bonds, and they'll all be single bonds. So our next step will be to write out our valence electron configuration, in particular for our central atom first, so that we can know whether or not it has to go an expanded octet or hybridization, and then we can do our periphery atoms to do our overlap. Okay, so what we can see here is the valence is 4s, 2, 3d10, 5p5. Now I'm going to write the 3d10 closer to it. I still have to record them because they're there, but I didn't write out the energy level diagram for these because the electrons in the 3D will not be involved in any bonding. Only electrons in the valence energy level, the 4th energy level, are. So I wrote out its energy level diagram, and what I can see is that I need 3 bonds. So right now I can only form 1. So I have to have one of my electrons split, and it will be promoted to the D, and then I will hybridize the S, all 3 P's in the D. I don't have to keep back any P's for a double bond, so that's why my new orbital, since it's a hybrid of an S, all 3 P's in a D, is called an sp3d. And now I'll take my 7 electrons in the valence energy level, 1, 2, 3, 4, 5, 6, 7, and I can see that I'm left with 3 orbitals with only 1 electron. So now what I'll do is I'll write out the energy level diagrams for the chlorine so that we can do the orbital overlaps. Okay, so now I can take the first chlorine, which would be this one here, and I can overlap its 1 orbital with 1 electron and have it overlap with one of the hybrid orbitals from the bromine with only 1 electron. They'll form a new orbital holding those 2 electrons. The second chlorine can overlap, and the third chlorine. So now I know that it's going to be an overlap of a hybrid with a P, a hybrid with a P, and a hybrid with a P. So that helps me to know the shape of my new orbitals. So I'll just write down my nuclei for the 4 atoms involved in this molecule. And so now for my first chlorine and the bromine, it's an overlap of a p orbital with a hybrid, and we know that the overlap of a p orbital with a hybrid gives us the candy shape. And then my second chlorine is an overlap of a p orbital with a hybrid, so it will also give me the candy shape. And the third one is also an overlap of a p orbital with a hybrid, so that's also a candy shape. And so I have this as my Okay, so we're going to look at this second example, and just like we said before, our first thing to do is to do our Lewis structure. So this one is a pretty straightforward Lewis structure. Okay, and then I need to write out my electron configuration for my central atoms. So I have two of them here, and my oxygen, so I have an idea of what's going on. So I'm going to call that carbon 1 and that carbon 2. So I know that carbon and so now it's going to undergo hybridization. Now because these two carbons have different bonds in them, they're going to hybridize differently. This one has 4 single bonds, so when it hybridizes, it's going to blend the S with all 3 P's. This carbon has 1 double bond, so as a result, when it hybridizes, I have to keep back a p orbital. So therefore, my carbon 1 will hybridize to form an sp3, and it will have 4 orbitals, each with 1 electron, all of equivalent energy. And my second carbon will form an sp2 orbital. It's a hybrid of 1 of the s, 2 of the p's, and 1 of the p's will not be included in the hybridization. Okay. Then I can have my hydrogen, and I can have my oxygen, and then for this carbon I also have 3 hydrogens. Okay, so now I can show my overlap. And so I'm going to have between the 2 carbons, I'm going to have a hybrid with a hybrid overlap. This P is kept back special, it's for the oxygen. And then my first carbon can bond with its first hydrogen, its second hydrogen, and its third hydrogen. My second carbon has a single bond to the oxygen, which is an overlap of a hybrid with a P, and then the second bond between them has to be between the side-by-side overlap of 2 p orbitals. And then the last orbital of the carbon will overlap with the hydrogen. So now when I go to draw, again I want to put my central atoms. That's my first carbon, that's my second carbon, there's my oxygen. And so if we look at this first carbon, it has 1 bond that is overlap with the other carbon of 2 hybrid orbitals. So an overlap of a hybrid with a hybrid looks like a fish. And then it has 3 bonds that result from the overlap of a hybrid with an S for each of the hydrogens. And so we know that the overlap of a hybrid with an S gives us generally the fish shape. Now my second carbon has an overlap of a hybrid with an S, so again we get the fish shape. And then finally we have a hybrid with a hybrid that looks like the candy, but then because it's a double bond and we have the side-by-side overlap of 2 p's, then my candy becomes the hot dog. Okay, and we could even go through this and we could label our bonds as sigma or pi.